The data on the screen isn't just numbers anymore. It's a violation of the laws we thought governed the dark, silent vacuum between the stars. I have been staring at these telemetry readings for 6 hours straight, the coffee on my desk long since gone cold, and the only conclusion I can draw is one that makes my stomach turn and my heart race in equal measure. We are looking at a deceleration event, a braking maneuver, or, if I am forced to remain within the rigid boundaries of conservative astrophysics, a momentum anomaly so profound that it threatens to rewrite our understanding of cometary physics. They are calling it 3I, Atlas. The 3I designation is clinical, dry, a catalog entry for the third interstellar object confirmed to have entered our solar system. But to me, and to the team currently scrambling to verify these astrometric points from the Cerro Tololo Inter-American Observatory, it is the ghost. It is the thing that shouldn't be here, moving in a way that nothing natural should move. To understand why I am shaking, why the scientific community is currently lighting up the secure channels with panic and excitement, you have to understand the history. You have to understand the baseline. We had 1I Oumuamua in 2017. That was the first. It was a tumbling, cigar-shaped enigma that accelerated on its way out, a non-gravitational boost that we eventually attributed, perhaps somewhat desperately, to the outgassing of hydrogen ice. It was a neat explanation, one that wrapped the anomaly in a bow of natural phenomenon. Then came 2I, Borisov in 2019. That was a comfort. It looked like a comet, it acted like a comet, it smelled like a comet. It had a tail, it had a coma, it had a chemistry we recognized. It told us, relax, the galaxy is full of dirty snowballs, just like our own backyard. But 3I Atlas. 3I is different. I remember the night of the discovery. It was the 1st of July 2025. The alert came from the Asteroid Terrestrial Impact Last Alert System Atlas, the station in Rio Hurtado, Chile. The system is designed to look for the rocks that might kill us, the near-Earth objects, NEOs, on collision courses. It sweeps the sky, looking for movement against the fixed background of stars. When the algorithm flagged a new trace, it was initially catalogued as just another hyperbolic comet, something from the Oort cloud perhaps, knocked loose by a passing star a million years ago and falling inward for a brief, fiery rendezvous with the Sunday. But the eccentricity was wrong. Eccentricity is a measure of how stretched out an orbit is. A perfect circle is 0. An ellipse is between 0 and 1. If it's 1, it's a parabola, an object that falls in, swings around, and has just enough energy to escape back to where it came from. Anything greater than 1 is hyperbolic. It means the object is unbound. It's a visitor. It's coming from the void with excess speed, speed that the sun's gravity alone didn't give it. 3I, Atlas, had an eccentricity of roughly 6. Let that sink in. Oumuamua was about 1.2. This thing wasn't just falling in. It was punching through our system like a bullet. It was moving at nearly 60 kilometers per second relative to the sun when we found it, way out past the orbit of Mars. And the trajectory was coming from the deep southern sky, slicing up through the plane of the planets at a steep angle. It wasn't interacting with Jupiter. It wasn't interacting with Saturn. It was a clean shot at the inner solar system. For the first few months, from July through September, we treated it as a high-velocity comet. We pointed everything we had at it, the Very Large Telescope, VLT, the Gemini South, and eventually the James Webb Space Telescope, JWST. We saw a coma develop, a fuzzy shroud of gas and dust. Spectroscopic analysis revealed it was rich in carbon dioxide, surprisingly so, and oddly depleted in water. That was the first red flag. Most comets are water-heavy. This one was dry, metallic, and spewing CO2. It suggested an origin in a system very different from ours, perhaps formed further out in the protoplanetary disk of a dying red dwarf, or stripped from a carbon-rich exoplanet. But chemistry is just chemistry. We can explain chemistry. What we can't explain is the motion. As 3I Atlas approached perihelion, its closest point to the Sun, on the 29th of October 2025, we expected it to speed up. That is Kepler's second law. As an object falls into a gravity well, it trades potential energy for kinetic energy. It must go faster. Based on its mass and its trajectory, we calculated its peak velocity down to the meter per second. We knew exactly where it should be at every second of its pass. Then came the data from the occultation event in early November, and the subsequent radar tracks as it swung back out. It was slow. It wasn't a massive error. It wasn't a glitch in the software. We checked the reference stars. We recalibrated the atomic clocks. The object was arriving at its predicted checkpoints late. In the world of orbital mechanics, late is a terrifying word. It implies a force. If you throw a ball in a vacuum, it lands exactly where the equation says it will. If it lands short, something pushed it back. We are talking about a drop in speed relative to the ballistic trajectory. We call it negative non-gravitational acceleration. Now, comets do this. This is the rocket effect. As the sun heats the icy surface of a comet, jets of gas erupt. If a jet points forward into the direction of motion, it acts like a retrorocket. It slows the comet down. We see this with comets like 67P, Churyumov-Gerasimenko. It's natural. It's messy. It's physics. But here is the problem. 3I Atlas isn't outgassing enough to account for this drag. We have the thermal images from JWST. We can calculate the mass loss rate. We know how many kilograms of CO2 and dust are leaving the nucleus every second. We can solve for the momentum transfer, $F equals ma$. The force generated by the sublimation of the ices we can see is roughly 10% of the force required to produce the deceleration we are measuring. Where is the other 90% coming from? I have been running the simulations for 3 days. I've tried adding a magnetic field interaction. If the object was highly charged and moving through the solar wind, the Lorentz force could theoretically create drag, but the solar wind density is too low, and the charge required on the object would be astronomical, physically impossible for a natural chunk of rock or ice. It would need to be a superconductor to hold that kind of charge, and comets are not superconductors. I've tried modeling it as a fluffy object, something with extremely low density, like cotton candy, so that the pressure of the sunlight itself, radiation pressure, is pushing it back. This is the solar sail hypothesis that was floated for Oumuamua, but in reverse. For Oumuamua, the light pushed it from behind, speeding it up. For 3I Atlas, as it leaves the sun, the light should also be pushing it from behind, accelerating it. But it is slowing down more than gravity allows. Wait. Let me correct that visualization. The deceleration anomaly was most pronounced during the approach and perihelion passage. It acted as if it was experiencing friction in a vacuum. And then, there is the anti-tail. In late October, just before perihelion, the images showed a spike of light pointing towards the Sunday now. Anti-tails are a known optical illusion. They happen when Earth passes through the orbital plane of a comet, and we see the large, heavy dust particles trailing behind the comet superimposed in such a way that they appear to point forward. It's a geometry trick. But we weren't in the orbital plane of 3I Atlas. The sunward spike on 3I was real. It was a physical structure. A stream of material was being ejected, or held, in the direction of the star. Some of my colleagues are arguing this is a swarm, that 3I isn't a single body, but a cluster of debris, and the center of mass is shifting, fooling our tracking algorithms. They suggest that what we are tracking as the nucleus is actually a cloud of smaller rocks, and the gravitational center is elsewhere. It's a comforting thought. It allows us to keep our equations. But it doesn't fit the light curve. The nucleus appears solid. It occulted a background star last week. A clean, sharp dip in light. A swarm doesn't do that. A swarm makes the star flicker. A solid body makes it wink out. 3I Atlas is solid. And it is breaking. I need to talk about the velocity vector again because this is what keeps me awake. The magnitude of the deceleration is tiny fractions of a millimeter per second squared, but integrated over millions of kilometers, it results in a positional shift of thousands of kilometers. It is currently 4 arcseconds away from where gravity says it should be. In my field, 4 arcseconds is the difference between confirmed and lost. Let's speculate. I am a scientist, but I am allowed to construct hypotheses, no matter how wild, as long as I test them. When I first started thinking seriously about what 3I Atlas might actually be, I kept circling back to the same uncomfortable triad of possibilities: dark matter, some exotic volatile we've overlooked, or something artificial. And every time I walked myself through each one, I felt that tug of war between the part of me that wants to stay grounded in established physics and the part of me that can't ignore what my own eyes, my own data, my own intuition are trying to say. I'm trained to be skeptical, trained to dismantle my own thoughts before anyone else does. But there are moments, rare but unmistakable. When the universe presents something that just refuses to fit into the neat categories I've relied on for my entire career. And with 3i, Atlas, that moment has been stretching for months. Hypothesis. A dark matter interaction was the first one people threw around half-jokingly in the early days, when the acceleration anomaly was small enough that we could pretend it would go away once we had more measurements. But even as I entertained it, I knew I was lying to myself. Dark matter doesn't behave like that. It doesn't care about the electromagnetic force, and it sure as hell doesn't exert drag on a comet-sized body on the scale of the inner solar system. I kept telling myself, look, if there were some dense clump of dark matter hanging around, we would have seen gravitational disturbances, anomalies in orbital motion, something. But there was nothing. Nothing, except the trajectory of this one object behaving as though it was plowing through molasses that no one else could detect. To get dark matter dense enough to cause that kind of drag, you'd have to rewrite the cosmological models from scratch, toss out everything from early universe baryon acoustic oscillations all the way to galaxy halo simulations. And I didn't have the arrogance to think 3i, Atlas, was worth ripping down the standard model of cosmology. So every time my mind tried to wander back to dark matter as a physical explanation, I had to stop myself. No, that wasn't it. It couldn't be. Hypothesis B felt more reasonable. Maybe the comet was composed of something we hadn't considered. Some kind of exotic volatile that sublimated so cleanly, so quietly, that it left almost no spectral fingerprint. I remember lying awake at night, thinking through every possible molecule we routinely ignore because they're either too rare or too unstable. Molecular nitrogen? But no, nitrogen betrays itself even in faint quantities if you look hard enough. And we did. My colleagues tuned instruments to absurd sensitivity levels. Still nothing. Helium crossed my mind more times than I'm proud to admit. But helium as a structural component of a comet is absurd. It's too volatile. It wouldn't survive millions, let alone billions of years, drifting through the freezing, irradiated vacuum between stars. I kept imagining it anyway. This ghostly, helium-rich body leaking invisible jets of gas that wouldn't show up in the spectra. But the physics just didn't cooperate. The formation conditions didn't make sense. The survival timescales didn't make sense. And the observations sure as hell didn't make sense. So then, inevitably, I arrived at the third hypothesis, the one I tried not to say out loud. The one I only joked about nervously with colleagues when we were 2 coffees past midnight and exhausted enough to abandon pride. The one we whispered in the break room, but made sure to delete from emails before hitting send. Hypothesis C. Artificial origin. Even saying it now makes something in my chest tighten. It feels like stepping over a threshold I'm not supposed to cross as a scientist who prides himself on restraint. But the data has a way of dragging you where you don't want to go. Look, if you wanted to scout the solar system, really scout it, you wouldn't approach at 60 kilometers per second and just whistle past the sun like a tourist taking a quick detour. You would brake. You would slow yourself. You would try to shed velocity in a controlled way. Try to give yourself time to study whatever you came to study. So when I looked at the deceleration curve, when I overlaid it against solar radiation pressure and conventional outgassing models and nothing matched, a part of me started whispering, what if the braking is intentional? What if it's controlled? What if it's engineered? And then came that damned image. The 16th of November 2025, an amateur astrophotographer from Japan, Satoru Murata, bless him, managed to capture time-stacked exposures with such clarity that when I zoomed in, I felt my whole body stiffen. Jets. Multiple jets. Material spraying from different points on the surface like tiny cosmic thrusters. Natural comets do this, sure, but not like that. Not in collimated, needle-like beams that look more like controlled plumes than chaotic bursts of sublimation. Real cometary jets diffuse into space, spread out, disperse. These didn't. These looked purposeful, precise, like someone was using them to stabilize a tumble or correct a trajectory. I stared at those jets for hours, telling myself I was projecting human intent onto natural patterns. But I couldn't shake the feeling that what I was seeing had a structure underneath it, a mind behind it. Then there was the anti-tail, the sunward tail that shouldn't exist unless something unusual was happening, and the public latched onto that immediately. Why does it have a tail pointing toward the sun instead of away from it? I listened to the press conferences where we patiently explained that anti-tails happen when dust spreads in the orbital plane and perspective plays tricks on us. But this one felt different. Too crisp. too narrow, too aligned. If it wasn't dust, if it was exhaust, real exhaust, then suddenly everything else clicked into place with a clarity that made me almost nauseous. When the deceleration data started lining up in a pattern correlated to solar distance, I felt the hair on the back of my neck stand straight up. Radiation pressure falls off with the inverse square of distance. Everyone knows that. But the magnitude of the deceleration we were observing didn't match standard radiation pressure. It was close, but off by a coefficient that made no sense for any known material. It was as if the object was reacting to sunlight, adjusting itself non-linearly, as though it were using the sun's light as part of a feedback mechanism. A light sail? A magnetic sail? Something that could sense the solar wind, brace itself against it, and bleed momentum in a directional way? I tried to tell myself it was just a mathematical coincidence, but the more data I fed into the models, the more the curve insisted on its own intention. By early December 2025, the object was on its way out past 1.8 AU, already dimming faster than we could compensate for, slipping away from us like sand through fingers. I can't describe the frustration I felt watching it fade. We knew it was the most important interstellar object we had ever detected, possibly the most important object in the history of astronomy, and we were losing it. The European Space Agency's Comet Interceptor mission, which could have been perfect for this, was sitting idle, stuck in an L2 parking orbit, not yet configured or fueled for the maneuver it would have needed. The timing was just wrong. Painfully wrong. And every night I lay awake thinking, humanity just let the answer to one of its oldest questions drift past it into the dark. We weren't ready. We were so goddamn close, and we weren't ready. The composition deepened the mystery. That high nickel content kept bothering me. The spectroscopic readings from the VLT showed ratios that didn't match chondritic meteorites, didn't match icy bodies, didn't match outer system fragments, didn't match anything I could classify cleanly. It wasn't pure metal, not by a long shot, but it had an alloy-like fingerprint, something that reminded me of corrosion patterns on refined steel. I'm not saying it was a hull. I'm not reckless enough to jump straight to that conclusion. But if you had built a spacecraft, and if it had wandered the interstellar medium for 1 billion years, weathered by dust impacts, cosmic rays, micrometeoroids, and ionized gas storms, then its surface might start to look very much like what we were seeing. Pitted, oxidized, metallic but uneven, like a relic. And then came the Mars data. I can't explain how surreal it felt to use a completely different planet as a triangulation node for an interstellar object. The ExoMars Trace Gas Orbiter managed to catch it in a few frames, tiny, blurry, almost hopelessly faint, but enough to measure parallax. And parallax doesn't lie. If Earth-based observations had been wrong, if the deceleration had been an illusion or an artifact, Mars would have exposed it immediately. But Mars didn't contradict it. Mars confirmed it. When the numbers came back, I remember staring at them in silence, the lab around me buzzing with chatter I couldn't hear. It was real. The slowing was real. Whatever 3I Atlas was, whatever was happening to it, the universe wasn't going to let me wave it away anymore. As the object kept moving, it forced me to revisit questions about its structure. Was it tumbling? Yes, but not randomly. The spin seemed to shift in response to solar intensity. Not in a perfectly engineered way, but not in the sloppy manner of natural torques either. It reminded me of a damaged drone trying to maintain stability with partial thruster functionality, correcting itself, overcorrecting, compensating again. Every adjustment had an almost desperate quality, controlled but imperfect. If it was artificial, it wasn't pristine. It was old, very old, maybe older than human civilization by orders of magnitude. I kept asking myself, if this thing is artificial, where is the signal? Where is the transmission? Where is the beacon that says, we are here? But then I would look at the deceleration curve again, and I would hear a different possibility whispering at me that maybe it wasn't designed to talk to us. Maybe it wasn't designed to talk at all. Maybe it was never meant to be found by another civilization. Not intentionally. Perhaps it was a derelict, a lost probe drifting through the galaxy, performing whatever program it was originally assigned, slowly degrading over eons. Or maybe it was an automated scanner, never meant to stop, never meant to communicate, simply built to observe and move on. Or, and this thought chilled me whenever it surfaced, maybe it wasn't trying to communicate because it wasn't active anymore. Maybe whatever intelligence built it was long gone, extinct, erased by time, and 3I Atlas was nothing but a fossil drifting through space, performing reflexes encoded by a species that no longer exists. There were and still are moments when I try to force myself back into the comfort of natural explanations. I remind myself that comets surprise us all the time. I remind myself that outgassing can be asymmetric, that nickel-rich bodies can exist, that our models of interstellar formation aren't perfect. I repeat these things like a mantra, grounding myself in the familiar, but the truth is that every time I look at the data, the unease creeps in again. Not because I want it to be alien, but because I can't shake the sense that nature wouldn't bother being this theatrical without a reason. The jets, the anti-tail, the anomalous deceleration, the composition, the controlled-like spin, each one alone could be explained. But together they form a pattern that keeps poking at my skepticism like a finger tapping on glass. I keep staring at those last measurements, letting them sink into me the way a final goodbye settles in long after the moment passes. And as I sit with them, I feel something I didn't expect. Not fear, not excitement, but a kind of hollow curiosity, like I'm standing on the edge of a cliff, trying to see where the land ends and the air begins. Because this isn't just an object anymore. It hasn't been just an object for months. It feels like a presence now, a kind of visitor that wandered into our neighborhood, glanced around without saying a word, and is now quietly slipping away while we're still trying to understand who or what it was. We are now closing out 2025, watching 3I Atlas glide toward the orbital path of Jupiter like a dim lantern drifting slowly into fog. One observatory after another is losing it, each one reporting, almost apologetically, that its brightness has dropped just below what their instruments can detect. Every time another one fails to see it, there's this strange tug in my chest, like losing track of someone in a crowd, just when they were about to turn around and say something. And I keep wondering what I'm going to feel when it finally disappears completely. When the last telescope, the last sensor with the last bit of hope left in it, points at the patch of sky where 3I Atlas should be, and comes back empty. Will I feel relief because the mystery is over? Or will I feel like I watched the universe whisper something and I stayed silent, as if I didn't have the courage to whisper back? All I know is that something passed through our solar system. Something real. Something tangible. Something that did not behave the way the universe normally behaves. It slowed down when nothing slows down out there unless something makes it slow. It brightened at times when there was no good physical mechanism to explain the brightness. It rotated in ways that defy the patterns we've built our careers assuming. And every time it did something unexpected, I had the same uneasy sense that whatever it wasn't just tumbling blindly through space. It was aware, maybe not in the conscious sense, but in the sense that it responded to forces we never detected. As it fades into the darkness just beyond the orbits of Mars and Jupiter, I keep thinking that we weren't looking at it. It was looking at us. Or at least, that's what it felt like, though I'd never admit that in a scientific paper. I don't think any of us would. But there are things you feel privately that no dataset can capture. And sometimes those unspoken impressions stay with you longer than the graphs, the measurements, or the peer-reviewed arguments ever could. So, what happens next? That's the question echoing through every lab, every observatory, every late-night Slack channel where astronomers cling to their caffeine and their uncertainty. The object is heading for a dynamically meaningful pass past Jupiter. Not close enough for a moon-sized encounter, but close enough for Jupiter's monstrous gravitational field to have a say in what happens to it. In March 2026, it will pass about 0.36 AU from Jupiter's orbit, and at that distance, Jupiter can either act as a slingshot or a net. So, we are running the numbers over and over, on different models, with different assumptions, and we're trying to figure out which one of those two Jupiter will be. Will it accelerate 3I Atlas even more, giving it the final push that flings it permanently out of the galaxy? Or is the deceleration we're seeing real enough, strong enough, persistent enough to change its fate? Because here's the truth I keep circling back to. If the speed drop continues, if the drag remains steady, however faint, there is a non-zero chance that 3I Atlas won't escape. It could slow just enough to fall into a long, thin, highly elliptical orbit, one that might swing it back toward us in a decade, a century, or even 1,000 years. That possibility keeps me awake at night. Not in fear, but in a kind of awe. Because if that happens, if it stays, everything changes. The entire scientific world shifts. Suddenly this visitor from another star system becomes a neighbor, a recurring traveler on a path we can predict. If it returns, we can intercept it, study it, touch it. Maybe, if the universe has a sense of irony, even land on it. But another part of me knows something else is possible. If the drag we've measured is just a transient effect, some exhausted burp of gas from a dying comet, some last exhale from a fractured refrigerator-sized lump of ancient ice, then all of this hope collapses into nothing. If the drag stops, if that faint deceleration fades, then 3I, Atlas, will fall out of the gravitational well like a marble rolling off a hill. It will accelerate again, pick up the speed it briefly lost, and vanish into the distant constellation of Libra, never to be seen again. Just a ghost passing through, leaving us with more questions than answers. I keep pulling up the most recent light curve, watching the trembling line settle into something steadier. A 5.4-hour rotation period is what we're working with now. But what unsettles me is not the period, it's how the amplitude of that rotation is shrinking. Most comets spin up. Outgassing nudges them, uneven jets push them, and the Yorp effect slowly accelerates their rotation over time. But 3I Atlas isn't speeding up. It's slowing down. The wobble is decreasing. The axis is stabilizing. It's rotating more cleanly, more predictably, more smoothly. It is damping its spin. I can't pretend that doesn't disturb me. It's acting like a ship that has just finished maneuvering and is now leveling itself out. I hear myself think it before I let myself say it, and the words feel like they don't belong in my mouth. Not as a scientist, not as someone who has spent years telling students to resist the seduction of extraordinary conclusions. But the data is the data. The light curve doesn't lie. It slopes down where it should slope up. The object is stabilizing instead of destabilizing. And that is not normal. Sagan's words echo every time I let my mind drift toward the possibility I swore I'd never entertain. Extraordinary claims require extraordinary evidence. And we don't have extraordinary evidence. Not yet. We have oddities, coincidences, anomalies that can be explained if you stretch your imagination, but not your equations. We have a comet that behaves slightly too intelligently for comfort, but not intelligently enough to call it anything other than an anomaly with a raised eyebrow. The tail points the wrong way sometimes. The composition has more metal than it should for something born in a distant star system. The rotation is wrong. The brightness is odd. And all of these things could be nothing. All of them could be perfectly natural but poorly understood phenomena. But when you see all of them together, in one object, in one place, all at the same time, it becomes harder to shrug and say, coincidence. I keep replaying the moment we first detected it, when its trajectory seemed almost too clean, too straight to be natural. I didn't think much of it then. Interstellar objects are rare, but not impossible. But now, watching it fade, watching its last whispers of light vanish into the dark behind Jupiter's orbit, I feel like I'm standing in the doorway watching someone leave without telling me who they were. The silence around this object has felt intentional, not in the sense that something conscious was withholding information, but in the sense that nature itself was refusing to reveal its secrets. Like the universe dangled this strange little enigma in front of us and then took it away right when we were finally beginning to ask the right questions. Every night since the brightness began to fade, I've gone outside after my shift, stood in the cold, and stared at the patch of sky where I know it is, even though I can't see it with my own eyes. And I try to imagine what it must feel like for something to drift alone through the void for millions of years, brushing past one star after another like a wandering pilgrim, only to stumble into a solar system full of creatures who can't decide if they're ready to understand what they're seeing. Maybe that's why I feel uneasy. Maybe that's why I'm not sure if I want it to stay or to go. Because if it stays, we're confronted with the responsibility of engaging with it, of studying it, explaining it, possibly rewriting some part of what we believe about the universe. And if it leaves, we're left with a mystery we can never solve, a door the universe briefly opened and then quietly closed. And in that uncertainty, I realize something else. I'm not afraid of the object. I'm afraid of what it means to be the species watching it. We're like children pressing our faces to a window, trying to understand something far older and stranger than we are. So I wait, I run more models, I check more data. I stare at the faint slope of a graph that shouldn't look the way it does. And every time I look at it, I feel that same strange sense that something out there moved with purpose, not conscious, maybe, but purposeful in a way we aren't used to seeing. I don't know whether 3I, Atlas, is a comet, a fragment, a failed planetesimal, or something no one has the vocabulary for yet. But I know this. We were changed by seeing it. And whatever happens next, whether it escapes into the silent dark or circles back one day like a returning traveler, I will never again look at the sky the same way. Because now I know the universe is watching back. But I cannot shake the feeling that we are the ants on the anthill, and someone just threw a stone at us to see if we would notice. We noticed. We just don't know what to do about it. The verified data points are these. Origin: interstellar eccentricity is greater than 6. Perihelion, the 29th of October 2025, distance 1.4 AU. Anomaly: non-gravitational deceleration of order 10, negative 5 meters per second power of 2. Morphology: sunward, anti-tail persisting post-perihelion. Current status: outbound, fading, magnitude 10.2. The interpretation of those points is where the war is being fought. The Dust Bunny camp argues for a fragile aggregate of ices that is shedding mass in a way we haven't modeled. The Exotic Physics camp argues for modified Newtonian dynamics, MOND, or some dark matter interaction. And the Technosignature camp, well, they are mostly silent, publishing on preprint servers, pointing out that if you eliminate the impossible, whatever remains, however improbable, must be the truth. I am looking at the screen. The dot that is 3I, Atlas, is just a few pixels across. It is billions of years old. It has traveled light years to get here. It dropped into our gravity well, looked around, slowed down, and is now leaving. If I were a scientist on a generic, inhabited planet, and I detected a probe from another civilization, I wouldn't expect it to broadcast, "Hello." I would expect it to behave with purpose. I would expect it to correct its course. I would expect it to sample the environment. The speed drop of 3I, Atlas, is the single most baffling astronomical event of my career. It defies the simple ballistic elegance of the celestial mechanics I have taught for 20 years. It forces us to add terms to the equation that we cannot define. I'm going to brew another pot of coffee. The latest telemetry from the Deep Space Network is due in 10 minutes. They are pinging it with goldstone. If we get a radar echo, if we can resolve the shape, we might know. If it's a rock, it's a rock. But if it's smooth, if it's flat, I am terrified that we will find nothing. And I am terrified that we will find something. The universe was quieter when we thought comets were just dirty snowballs. Now, every shadow moving against the stars looks like a question mark.